Everybody to our next talk in the series. One word Malaysian seminar. The speaker today is Wotao Yin from UCLA. Good morning, Wotao, and thank you for accepting our invitation. This is an effort. I mean, it's very early, but we are happy that you agreed to give a talk in the framework of the seminar. I will just say some words about the rules of the game. So we will take questions during the talk. We will take questions at the end of the talk. Please raise your hand. This is an option offered by Zoom, or just write in the chat. I will unmute your microphones, and you can ask your questions to Wotao. And Wotao, needs no introduction. He's a professor at UCLA, working also for some important Chinese company and doing optimization a lot with algorithms, theoretical investigations, numerical experiments. He's a well-known mathematician in our community. So, Wotao.
Okay, thank you, Radu. Thank you, all the organizers, reorganized, for making this series available. And I think this is of course, a great event at the difficult time. Also, thank you for coming. Thank you for your attention. Good morning, or good afternoon, good evening to people at different places. Yes, just about myself. I'm from UCLA Math Department. I'm currently on leave, on a short leave at Alibaba, and over there, I'm studying optimization and also supporting a team who works on cloud computing scheduling, so we can keep the cloud running during the difficult time. So I'm going to talk about the scaled relative graph. This is the joint work with brilliant people. Ernest Ri, who's somewhere here. I just saw him in the list, and he's at Seoul National University. And Robert Hannah, who graduated last year from UCLA, who's now working at Citadel. This work has been submitted and is under the second round of review. Okay, let's begin. So just assume all of you can see the slides. So many optimization methods are examples, are special cases of fixed point iterations, and convergence of fixed point iterations usually are analyzed through a series of inequalities. So inequalities are rigorous and they are relatively easy to verify, but they may be unintuitive from time to time. So today we're going to introduce an alternative 2D geometric tool to analyze contractive and average fixed point iterations. And then the tool is a signature of the fixed point operators and other operators, and which are analogous, like how eigenvalues are signatures of matrices. So we are going to use some diagrams to visualize and concisely capture and communicate the core idea, core insight of a proof. And under some conditions, it'll serve as rigorous proofs for convergence. And another advantage of this tool is to give constants, which cannot be improved without further assumptions. Okay, so let's begin with a sample result. Suppose f is a mu strongly convex and L Lipschitz differentiable functions. Mu and L are positive, L is larger than mu. Then this gradient descent iteration will converge linearly to a minimizer of f. And the rate is given by this formula, and this rate cannot be improved without further assumptions. By the way, all the facts, all the results are stated as facts when we provide just an alternative proof. So basically, these are known results for which we reprove with the geometric tool. And the theorems will be new results in this talk. Okay, so this result can be illustrated by this diagram. In the first diagram, there's a set which corresponds to the set of gradients where the function is from, where the function is a set of strongly convex and elliptic differentiable functions. And then this set kind of goes through a series of transforms corresponding to the gradient descent iteration. And this set going to be transformed into this shaded region. And then finally, we find the smallest disk centered at the origin that encloses the set. And the smallest disk will have a radius r. And depending on the value of alpha, mu, and L, this shaded region may be a little to the left of the center or maybe a little to the right of the center. Therefore, the R going to be equal to this maximum. Okay, so this is just, so far the diagrams are just illustrations. We're going to define the shapes. We're going to explain the transforms, and then finally make the geometric arguments as rigorous proofs. But this gives you a sample of the result. Of course, geometric illustrations are not new. It has been used on many things, in particular on fixed point iterations. The earliest work that use such illustration is Eckstein's thesis and his paper with Bersikas. Recently, when people use geometric illustrations to come up with tight constants, especially for linear convergence, they often use a series of graphs, a series of diagrams, which are similar to what we're going to introduce. Specifically, I want to mention the lecture notes by Pontus. I think Pontus is somewhere in the audience, and his paper with Stephen Boyd, as well as this follow-up paper, and also on tight linear convergence rates. So of course, many people have been using geometry. It is behind many of the results that are eventually written down as algebraic proofs. Okay, so a special feature that contribution of this talk is to make diagrams rigorous as proofs. So optimization methods are often fixed point iterations, and we say a point is fixed point with respect to a operator T mapping from a Hilbert space to the Hilbert space. If T applied to this point, give the same point. That is called a fixed point. So usually under convexity and under regularity conditions, many optimization methods can be written as a fixed point condition. And then this condition can also become a algorithm. For example, if you minimize a convex differentiable function, then the minimizer satisfies this fixed point iteration, which basically says after canceling x star, grad f at x star should be 0. If you minimize the sum of two functions where the first function has a proximal map and the second function is differentiable, then you can get this so-called forward-backward fixed point iteration, or forward-backward fixed point, or proximal gradient fixed point. This alpha is the step size. If you have this problem in the ADMM form, where you have two variables x and y, which have their own objectives and get coupled through a sequence of linear constraints, and then an ADMM can be written in a very abstract form, still as a fixed point iteration. So here, I think the resolution issue causes the missing of the division sign. This is 1/2. And these operators are certain reflection operators. I will come back to them later. Now, this fixed point is given in Z star. It is not in X star or Y star. It is a encoding of a primal and dual solution. So once you get the Z star, you can recover both X star, Y star, as well as the optimal Lagrange multipliers. So here are just some examples to say that optimization often meet fixed point iterations. Now, such fixed point iterations can be analyzed in a standard fashion. There are lots of exceptions, but here are two common steps. The first step, we prove that this fixed point operator T is either contractive or averaged. And then applying standard arguments, we're going to show that this iteration converges linearly or converges sublinearly at a certain rate. So let me use 2 slides to illustrate contractive operators and average operators. So even though I have not defined SRG, the graph yet, but let me still use this picture, which is relatively easy to understand, to illustrate the set of contractive operators. So basically, imagine that this point, this origin somehow represent the solution you're after. So this says if you start with a distance 1 on the circle toward the solution, applying 1 iteration of this operator will bring you to a circle that is closer to the solution. And you keep doing this, and every time there's a guaranteed amount of decrease. L is the ratio of that decrease. So Banach fixed point theorem says if T is contraction, or this operator T is contractive, that is, T is L ellipse with a constant L less than 1, then iterating this operator will converge linearly to the unique fixed point, X star, of T. Now this is the illustration of average operators, and average operators are less well known compared to contractive operators. So average operators is illustrated this way. So notice that some point on this circle is very close to 1. So this is the circle centered at 1 minus theta with a radius theta. And theta is strictly between 0 and 1. Because part of the circle touches 1, it's no longer a contraction. Iterating this operator may not guarantee a geometric decrease to the solution. However, if we properly, I have not defined this graph, but later on I will define this graph. But let me just say that when you are close to 1, you're not necessarily decreasing the distance to the solution much, but you can decrease the fixed point residual a lot. So here is this Kornoselsky-Mann theorem that states the convergence of averaged operators. If T is theta average with theta between 0 and 1, and assume T has a fixed point, then the fixed point iteration converges to one of the fixed points of this operator T. We cannot say the rate of xk to a solution. However, we can say that the rate of residual decreases at least like 1 over k little o. Okay, so with the standard results, we know contractive operators has linear convergence, average operators has sublinear convergence. Now the task we're facing is to tell whether a given operator is contractive or averaged. So to do that, we need to understand how T is formed. T in optimization is usually built from several operations like scaling, addition, and inversion of standard operators like identity, matrices, gradients, and subdifferentials of functions. Here's an example. The forward-backward splitting operator is built as the gradient descent operator and the proximal point operator. The proximal point operator, proximal point mapping, can be written in this way, which depends on the subdifferential of f. And this is at least good for certain convex, proper closed convex functions f. So what we're going to do today is, in terms of operators, we're going to look at several different forms of like this with different operators A and B. So the original A and B original operators are from your problem, and then the operator splitting or your optimization algorithm represents a transform T, which applied to A and B give you a new operator T. This whole fixed point operator is called T. And then we say through, say, algebraic proofs, analytic proofs, we say T belongs to either the contraction or the class of average operators. Therefore, have certain convergence guarantees. And our goal is to represent this, reconstruct this in terms of geometry. We will draw 2D shapes for A and B separately. This G stands for graph, so 2D shapes. And then we're going to create a new shape out of the transforms of T. And then we're going to visualize whether this new shape is enclosed in the shapes of either the contraction or the average operators that I just shown you. By definition, when the first row holds analytically, we also have the second row. But for a certain class of operators, including L, including this contraction and average operators, when this iteration holds geometrically, it turns out this relation also holds algebraically. Therefore, construct a formal proof. Okay, so now let's formally define the skeletal relative graph, or SRG, of an operator. Because we deal with subdifferentials, and these operators can be multivalued. So to define this operator, we use differences. We pick two arbitrary inputs x and y, and then from the images, pick u and v. And then we plot a point in the 2D plane and borrowing the definition of a complex number. So R, the radius of the complex number, is the size of the change in the results relative to the size of the change in the inputs. And the rotation is measures how much the change in the output lined up with how much change in the input. And the angles are have plus and minus. Therefore, on the complex plane, this point will be symmetric. So as an example, the simplest example will be identity operator. And that identity operator will not cause any size change and will not rotate. Therefore, the z corresponding to the identity operator, no matter how you choose this x and y, will always give you 1, 0, the unit point on the complex plane. But in general, we have the z going to depends on x and y. Depends on how you choose x, y, and how you choose the outputs. So therefore, we simply form a graph from all such points z by looking at all different points in the domain, as well as their outputs. So this becomes a set. And also, we're going to include infinity as an artificial point if and only if there's a point where A is multivalued. So if A is for example, the subdifferential of L1 norm, it will include the infinity point artificially. And we include that to deal with inversion. So because we often focus stating results, focusing on operator classes rather than specific operator, we also define the graph of operator classes as just the union of the graphs of individual operators, individual members in this class. So here comes 3 examples of SRG. Projection to any line in R2 going to form SRG, that is a circle between the origin and 1. If you have a 3x3 diagonal matrix where the diagonal entries are 1, 2, and 3, and you draw the graph, it will have this very special shape that connects 1, 2, and 3. So in general, for 1 or 3-dimensional and higher matrices, the SRG of the matrix will include the spectrum of the matrix. So this is a little more unusual example, and this is L2 norm without the square. And then we look at the subdifferential as a set-valued operator. You draw the SRG, it will be the right side of the complex plane without the imaginary axes, but including the 0, as well as the infinity. So in general, you can draw these graphs in two ways. You can either use the definition, or you can, for example, sample lots of points, write a script in MATLAB and sample the points and plot them. Usually it's very easy to figure out the shape. But today we focus more on the operator classes, since most of the theorems about optimization are stated with the operator classes. The first operator class we look at is the mu strongly convex monotone operators. Here, mu can be 0 or positive, and the graph gonna be the right side of the vertical line at mu. And this set also includes multi-valued operators, therefore infinity is also included. A subset of such operators is the subdifferential of mu strongly convex functions. Of course, when mu is 0, this is just a standard convex functions. A very different shape of another very often used class of operators is this shape between 0 and 0.1 minus 1 over beta. So this represents beta co-cursive operators. A large set of examples, subset of examples of such operators is the set of gradients of 1 over beta Lipschitz differentiable convex functions. So even though these functions are differentiable, I'll still just use the partial sign for simplicity. So finally, these are two graphs you have already seen, the Lipschitz operator, the theta average operators. So recall, if you have a operator T that generate a graph, within this shape, we hope that this operator T also belongs to this class. If you have operator T generate a graph within this shape, we hope that that operator also belongs to theta average operators. But in general, so we have to discuss whether this is true or not. That is, whether operator relationship corresponds to a relationship in the geometry. Specifically, if we have an operator that is either contraction or an average operator, do we have the graph, the inclusion of the graph? This belongs to. This is a subset rather than belongs to. So this forward direction follows from the definition. Okay, so if a larger set, you draw the graph. Of course, the graph is larger. The converse generally is not true, because a smaller set can generate the graph just look like the larger one. For example, this is a smaller set, but the smaller set generate the same picture. Therefore, it's missing lots of the components. So if you have an operator taken from this class, but not that class, you're gonna get maybe a point or a subset in this graph. However, that graph enclosure in this case does not mean the operator belongs to this. Does not necessarily mean the operator belongs to this class. So we need some quantifications. But fortunately, this inclusion, the converse direction also holds for important class like the contractive operators and theta average operators. That's why we have this definition, SRG4. Essentially, a operator class A is SRG4 if this class can be fully characterized by the SRG. So the direction gonna holds both ways. So given SRG4, then we can basically check this membership by verifying the containment in the graph. And we have a sufficient condition for many operator classes that are SRG4. We say when a operator class is defined by one homogeneous equation, including inequalities of the change in the output, the change in the input to norm squared, as well as the inner product, then this operator class is SRG4. In particular, the monotone operator, the strongly monotone operator, the beta co-cursive operator, an L-Lipschitz operator, including contractive operator, and theta average operators are all SRG4. So SRG4 allows us, once again, to check membership. Okay. So next, we move on to show how transforms of operators map to changes in their SRGs. So these are the tools for us to analyze the convergence of many fixed point iterations. So here I list several of these tools. On the left are the SRGs of the transformed operators, where the transform uses operations in the operator space, such as scalar multiplication and addition and inverse. On the right are the Minkowski type operations to the sets. For example, this one means beta applied to every point in this set multiplied by alpha. So this is Minkowski type addition. And this is set inclusion. And I will introduce this later. And this is addition of Minkowski type. And this is multiplication of in Minkowski type. Everything on the right-hand side, including this inversion, are done just like they are done on the complex plane. So let me mention this one and that one because I'm not going to come back to them. So this says, well, under suitable condition, the conditions are both A and B are SRG4. Then the graph of the intersections of these two operator classes equal to the intersection of their graph, the intersection of the graphs. So one particular use of this is, suppose you have a operator that is both co-cursive and strongly monotone, then you will encounter this class. Right? You will encounter this intersection. So you can easily draw their graphs by intersecting their own graphs. So this condition holds, this equation holds when both A and B are SRG4, and either A or B has so-called a chord condition. So I will not explain that because I will not use this property in the rest of the slides. And I will come back to these specific tools later. So let me start with the first tool and see how it can be used to help prove theorems. So for any alpha and beta, the graph, again, of the operator, transform operator equal to a transform on the complex plane. So it can be used to prove the fact that I stated on the third slide. So recall, if F is strongly convex and Lipschitz differentiable with parameter mu and L respectively, then gradient descent converge linearly at this rate. Now this can be formally proved by the geometric arguments corresponding to these diagrams. So we first plot the SRG of the gradients of these convex functions. And this is the notation from Nestrov's book. So this is the set between, this is the disk between mu and L. And then we're going to apply the transforms. The first transform we're going to apply is this minus alpha. So minus alpha multiplied to every point here, going to transform this disk to that disk. This disk on the right side of the plane, this disk now is on the left side of the plane scaled by alpha. And then we're going to add the identity. Whenever we add the identity operator, it's right shifted by 1 unit. Therefore, this disk is going to move to minus 1 over 1 minus an alpha L and 1 minus alpha mu. The final step is to find the smallest contraction, smallest set corresponding to this contraction operator class. That is the smallest set centered at the origin with the smallest radius to enclose our set. So this enclosure can be written like this. And because this set, now R, is SRG4, therefore this enclosure implies this membership. That is, use any mu strongly convex and ellipse differentiable functions gradient to generate a gradient descent operator will be, and this operator will be our contraction. Okay. So that was a rather simple tool, and that tool can help us basically understand lots of the operations that does not involve any resolvent or any proximal. Once we involve proximal, we're gonna need some inversion. And the inversion makes this even more interesting. Okay, so let me first mention this operator inverse. So A stands for an operator or a set of operators, an operator class. This inversion is applied to every single operator in that class. So imagine that we have input x to this operator A and the output is u. The inversion basically means the input is u, the output is x. And because A can be multi-valued, this inverse is always well defined. On the right side is the graph. And the graph has lots of points. It consists of complex points. And this is the complex inversion. Now, what does this inversion look like? So this is also known as a geometric inversion, which is also called a reflection in the unit circle. So this transform takes point z to this inversion. Now for convenience, I use the convex conjugates there so that this transform preserves the angles. And then the product of the distance of z to the origin and inverse to the origin will be 1. So this length multiplied by that length is 1. So this is how inversion is defined. Now let's move this point z. If you move this point z on one circle, the inversion will move on the other circle. Okay, so in particular, when the input is on the unit circle, the output is also on the unit circle. Interesting thing is, if you take an input at the origin, and then it get mapped to infinity. And then if you move the input on a circle through the origin, and then get to be mapped to a straight line. An even special case is if you map a point on a straight line through the origin, the point's going to be mapped to points on the same line. We say a line is a generalized circle with an infinite radius. So this inversion, this geometric inversion, is basically defined as a transform that preserve angles and map generalized circles to generalized circles. So this inversion can help us analyze operators involving the resolvent. So here's the fact. If A is monotone and alpha is greater than 0, then the so-called resolvent of alpha A, which is alpha A plus identity inverse, is a half-average operator. And this iteration, if has a fixed point, will converge to a fixed point at the sublinear rate. So this statement can be proved by 3 diagrams. So let's first draw the graph of monotone operators. Recall monotone operators going to have the mu equal to 0. Therefore, it's the right side of the plane, just right to the 0 imaginary line. And then you scale it by alpha, and alpha is a positive number. You get the same graph. And then let's do the translation. The plus one going to shift the graph to the right by 1 unit. And then we take the geometric inversion of this region that maps to this ball between 0 and 1. Specifically, 0.1 maps to 0.1, infinity maps to the origin, and this vertical line maps to the boundary of the circle. Now, the circle itself is the half-average ball. Therefore, such operator, this operator is a subset of, this graph is a subset of the graph of half-average ball. Therefore, this operator class is a subset of the half-averaged operators class. Now, if we strengthen the property, let's make it strongly monotone. Say mu is strongly monotone, where mu is positive number, then you're going to have a little gap here because this gap is alpha times mu. After shift, it'll create a little gap to the unit circle. And then after the inversion, you're going to create a little gap to the boundary of the circle. And now you recognize the circle is smaller. The circle is a subset of a contraction circle with this contraction factor. Therefore, under this condition, this iteration has linear convergence. Okay, and let me bring up a recent result by Pontus and Stephen Boyd. And this result can be proved by these diagrams. So again, some of the fractions are missing due to resolution issues. So here we have strongly convex function with L-Lipschitz gradients. Okay, so this is a smaller class than just being strongly monotone and 1 over L co-cursive. In fact, this class, I'm sorry, there's another typo here. So this picture is the picture of identity plus alpha times the set. Okay, so I'm drawing the picture for identity plus alpha applied to the gradient in this class, so which give you the set. The left side is 1 plus alpha mu, right side is 1 plus alpha L. And then we take the inverse, which gives you the proximal map of the set. It becomes a smaller ball. So this point, the right point, mapped to the left point here. The left point in the first graph mapped to the right point in the second graph. So this shows that this proximal operator of such a function is 1 over 1 plus alpha mu Lipschitz, which takes the larger point, the point that's further away from the origin. And then you can double the size and then left shift by 1 unit, which gives you so-called the reflection operator. This is the operator R in the ADMM slide. So after this reflection, then depending on these values, this point may be further away from the origin, maybe closer to the origin. Therefore, you're going to have a linear convergence of this radius. And also these scattered, these constants are tight because because we can actually come up with a example that attain these tight constants. So in this example, this point gonna give us a tight rate because it's furthest away from the origin, and this point gonna trace back to that point and trace back to this point. So when you draw this graph, you can come up with an example that attain the property corresponding to this point. And that example is the example that attains the tightness. Therefore, in general, tightness are pretty simple to obtain with these diagrams. So the next example I'm gonna mention is, this next tool I'm gonna mention is the composition. Well, this is because many important subclasses of fixed point iteration are built upon 2 or more operators.
Sorry, Wotao, there is a question.
Okay.
Let me unmute the microphone.
Yeah.
So Joe
I'm
Chen.
listening. Yeah. How are you? Yeah. I'm just curious. Your geometry theory is very interesting, but how to understand from the figure whether the rate is tight.
Okay, the rate is tight is preserved by the transform. So this is the graph that we generated from the members from this class. That is, every point in this set correspond to at least 1 instance from this class.
Mm-hmm. Yeah.
Okay. Then you're gonna usually pay attention to the boundary, because part of the boundary gonna be transformed both ways. It can be transformed forward or transformed backward, because these transform have the equality sign. So in particular, this point, this example gonna be an example that give you identity plus alpha times its gradient. Okay, this is gonna be a specific function that give you identity plus alpha times gradient. That's corresponding to this point. You're gonna be transformed to this point. Okay, the same example, then transform to this point, and then gonna be also transformed into this point.
Oh, yeah. For this particular example, I can follow your reasoning, but whether it's possible for all kind of fixed point iteration to see to find out the tight rate.
So if at least we can say the following: if the final property you're gonna state corresponding to an SRG4 class, okay, and that SRG4 class has tight enclosure on graph, then you can discover examples that attain the tightness.
Okay, thank you.
Yeah, thanks for the question. So we're gonna so let me state this theorem. This theorem says if SRG A and B are both SRG4, then excluding a very special case, we have this inclusion. The compositions, the Minkowski type of composition of these two classes will have a graph that encloses the Minkowski complex product of the two graphs. And when either A or B has the arc property that's stated below, then this inclusion becomes equality. So specifically, I want to mention that compose class A with B is not going to give you the same operator class as B compose A. However, under these properties, they have actually the same SRGs. And these conditions are sufficient, but not necessary. So this so-called arc property says, well, we say an operator class has the property if pick any point in the SRG, and you draw an arc, either the right arc that is centered the origin from Z to its complex conjugate, or the left arc. If either the left or the right arc still entirely in the SRG, then we say A has the arc property. So this property ensures the equality to hold. Okay, so let's try to use this tool. So here's a fact: for two closed convex sets that have a non-empty intersection, alternating projection method, and this iteration converges to some point in the intersection. This is a well-known result. Now, because projection is a special proximal point, special proximal operator, it is half-averaged. So this is a composition of two half-averaged operators. Therefore, we can use this more general fact from Ogura and Yamada back in 2002. So they say, once again, n theta stands for the class of theta average operators. Then if you compose a theta 2 average operator with a theta 1 average operator, then such an operator is theta average and up to this formula. And there's a division sign. So in particular, if you compose two half average operators, plugging theta 1, theta 2 both equal to half into this formula, you're going to give you 2/3 unaveraged. Now this can be at least illustrated using these two diagrams. So recall, half average operator is a disk between 0 and 1. Okay, so we're going to draw the Minkowski product of these two. We're going to draw Minkowski products of two half average operators. On the left, on this diagram, it's the the SRG times a Z that's picked from the circle, the boundary of the first ball. Now, if you vary Z, if you fix Z, then this little ball corresponds to this SRG transformed by Z. So Z scales and rotates this ball over there to this little ball. And then you take the union of such results, unionizing over Z on the circle, you're gonna get a set. The set is enclosed by the heart-shaped dashed line, which is called, and the set is called a cardioid. So the set is called cardioid. And then you can show that cardioid is a subset of the set corresponding to the 2/3 averaged average operator class. So in particular, this cardioid is gonna have a smooth boundary here. And this boundary is going to have a curvature that's equal to the curvature of this 2/3 ball. Okay, so this 2/3 ball is the disc that goes through that point, and smallest that still encloses the cardioid. So in fact, we with a summer student, Mengxin Huang from USTC, last year we showed that this result can be generalized to any theta 1, theta 2 between 0 and 1, and then the SRG of their composition is a region enclosed by a curve given in such a polar coordinate form. Okay, and then from this result, you can see that we can show that their formula is actually tight. Tightness was not given in this paper, but we show that the theta cannot be improved without further assumptions. So basically, we can characterize the boundary of this cardioid as well as the shape corresponding to other theta 1, theta 2. And then we can show that that this ball, so this theta going to be changed, to theta given by that formula. And that ball going to enclose this shape by just checking with the checking against the formula, because the formula is going to have a greater than sign, except at this point. And then you're going to calculate this curvature and their curvature match. That means if you use smaller theta here, and this gray ball going to be smaller, and you're going to cut into this heart shape. This is roughly how we show these theorems. So here's the one application. Now, let me show you another, I think, very nice application called plug and play. Plug and play basically replace an operator, such as the proximal operator of total variation in classical optimization methods, such as forward-backward splitting and ADMM, by a better denoising operator for image denoising. Examples of better denoising operators are block matching, 3D filtering, and neural networks. And they can be made a better denoising operator than TV, and they do not correspond to a proximal operator of a function. This is why they are called plug and play. Now, why are they used? Well, that's basically because these data-driven denoisers can be obtained when there's no sufficient data for training or time for training. So you can come up with a model such as forward-backward plug and play denoising, where using a H operator that turns a noisy image to a less noisy image and plug it into the forward-backward splitting framework that replaces the proximal operator. Now, in this iteration, F usually stands for data fidelity term, which encodes the physics and how the samples are made out of the image. H can be trained using neural networks or obtained from an existing nonlinear operator. So this is called plug and play. And plug and play was introduced by Venkatakrishnan et al. Back in 2013. And they have very good results. Here I steal some results from Stanley Chen et al.'s paper. This is the low resolution image. and we generate high resolution image using optimization with a regularity term. So these are other methods, which I won't mention, but plug and play ADMM with block matching 3D as one of the operators generate the best result. This is the cleanest image among all these images. So here's another example where the samples are single photons, are binary. When you have a 1, it means there are 1 or more photons that hit the point, hit the sensor at that point, 0 otherwise. And this is the image of Purdue campus. So plug and play ADMM with BM3D is compared to 2 other state-of-the-art methods. They all work pretty well. You can see a little noisy here, little noise there. And if you zoom in, you're gonna see that plug and play ADMM with BM3D has much better results. So plug and play methods have been used a lot today in signal processing and image processing. However, its convergence has been eluded for a long time. In particular, we cannot use standard operator splitting technique or assumption to analyze them because this denoising operator can be may not have.
Wotao, there is a question.
Okay.
So H is non-convex. H is an operator. I mean, yeah.
Well,
yeah, he's saying about this, I think. Yeah.
Yeah, well, I mean, actually explaining the assumption on H.
Okay.
So the question just came in time.
Yeah.
So H, it does not correspond to a function.
Yeah.
But one assumption that we can make regarding H is it's very close to identity operator. Okay. So remember, this H is to denoise, but this H is used in the iterative framework. It does not have to denoise in one shot. It reduces noise iteratively. So when there's small amount of noise, H should be very close to identity. The H can have a very weird shape, can have data-driven trained form, which can have all kinds of properties. However, you can always find a relatively small epsilon so that H is close to identity because H is not supposed to change the image too much. So this property is illustrated by this little set on the SRG. And this may not correspond, well, if the set corresponds to gradient of a function, yes, that function is convex, but for operators, it does not have to correspond to any convex functions. Also, this assumption can be enforced during, for example, training of neural network using so-called real spectral normalization, which is basically some power method embedded inside the training. So using SRG, we can very quickly prove convergence, at least in the following case. When f is mu-Stronic convex function.
This is not me.
Okay. All right. So f is Stronic convex functions with Lipschitz gradients. We know it corresponding to a contraction. Now, when you compose the contraction with that little ball inflates this contraction ball. So the entire operator, the plug and play operator, based on forward backward splitting, will have a larger radius. Now, if that radius is still less than 1, then this operator still have linear convergence. Now, whether this radius is less than 1 depends on the choice of parameters as well as the choice of step size in this form. So we give specific conditions when this can be satisfied. Now, plug and play operators is more successful with the ADMM. Is there a way to actually get rid of the annotation?
I don't know. I mean,
clear all drawings. Okay, here we go.
Good.
Okay. So plug and play is also often used with ADMM. It's actually generate better results. So we can replace either this proximal operator by H or replace that proximal operator by H. Both ways works. And we give conditions on how to make sure this is a contraction operator using like 5 diagrams. So you may want to compare them. So even if you have the same H and you have all the same parameters, it turns out they have the same fixed point set. Therefore, iterating them should converge to the same fixed point. However, forward-backward splitting is easier to implement because it uses gradient rather than proximal. Plug-and-play ADMM has much better results because it actually has, if you examine these formulas, you realize it converges for larger epsilon and wider range of alpha. So if you have some tuning time to tune it, you can easily tune it so that ADMM converges while F4 backward splitting does not converge, and ADMM give you better results.
Wotao, I have a question. Can you explain in which way do you combine this operator H with the ADMM?
So there's a transform I applied. So ADMM gets written compactly in this one line operator form.
Okay.
So this H exactly replaces the proximal in ADMM, and that ADMM has a constraint x equals y. Therefore, the ADM subproblem become a prox operator.
Okay. So you use the representation of Bertseca's Eckstein, the Dagger transfer algorithm?
Actually, here we do not involve the dual. We use the infimum post-composition.
Okay. Good. Okay, good.
Because you cannot define dual for this guy.
Okay, good. Thank you.
No problem. So finally, before you go, this is another set of applications. We can use SRG to give some high constants. For the same reason, we can use SRG to prove some impossibility results. So this impossibility results is regarding inversely Lipschitz operators. So inversely Lipschitz operators basically defined as such. The input change is upper bounded by a scalar times the output change. So if you plot the graph, it's actually the outside of the 1 over gamma unit ball, and 1 over gamma ball. Now, this set is a little weird. However, it actually contains an important subset. If you visualize there's a vertical line going through 1 over gamma, the right side of the line is actually the 1 over gamma strongly monotone operators. So basically, this says there are more inversely Lipschitz operators than strongly monotone operators. And strongly monotone operators often give you linear convergence. Therefore, the interesting question is, in some algorithm, if you were dealing with strongly monotone operators, can you replace it by more operators that are inversely Lipschitz and still obtain linear convergence? So this is related to definition called metric subregularity. I will not have time to define this, but let me just say that many audience probably more familiar with the error bound condition by Law and 10 back in '93. That's a condition basically says the size of the gradient is bounds the distance to the solution. So if you have smaller gradient, you have closer distance to the solution, which is a critical step in the proof of many linear convergence results. Okay, so so in many recent works, people have been relaxing either strong monotonicity to metric separate regularity, which is implied by inverse Lipschitz, or relaxing strong monotone, strongly convex functions to just to error bound to convex functions with error bound conditions, and still obtain linear convergence for gradient descent, proximal gradient method for backward splitting operator method and certain ADMM. However, this is not always possible. So here is a case where this is not possible and can be proved by 3 diagrams. So, so in order to show impossibility results, we're not showing impossibility for just one algorithm. We parameterize to make it a richer class of algorithms. And this algorithm class is Douglas-Rushford, which in convex setting is equivalent to ADMM. And we make alpha and theta scalars that can vary. And we use A and B to characterize the class where A is from and B is from. So we have a positive result and a negative result. So the positive result is known. It says if A is strongly monotone, because since it's strongly monotone, monotone no longer makes sense. So if A is strongly monotone and L lipids, and B is monotone, then for proper alpha, for sufficiently small alpha, when you fix any alpha and theta, this is going to be a contraction. Therefore, ADMM or Dawes-Rashford will have linear convergence. And you can let this class be, you can let this guy be B, this guy be A, or revert them. Both of them have linear convergence. And they're equivalent for convex functions in cases for ADMM is proved in these two papers. However, if you relax this strong monotonicity to the larger set, that is one of gamma inversely lipids, then no matter how small alpha is, you cannot guarantee this. There are always examples where linear convergence cannot be attained. This can be shown by 4 diagrams rather than 3. So this set is the intersection of the SRGs of these 3 graphs. This right side of the plane, inside of L ball, and this outside of 1 over gamma ball, which give you this little shape. Now, this little shape, take a look at its reflection, it's gonna give you this shape. In particular, this line segment is mapped to this arc A prime, B prime. And they are on the boundary, that's important. Now, this reflection gonna compose with that reflection. And because this set, both sets are, let me see, this set has the arc property, therefore the composition is actually equal. So this is equal sign. Now this guy compose that because they're both in the unit ball, but this guy is full unit ball. You're gonna compose into a unit ball. So you just do complex multiplication. You're gonna compose into the unit ball. Now this says, well, you're not able to guarantee that every instance of this composition of reflection operators will be contraction. Now that ADMM or that Dawes-Rashford is the average of this guy with the identity. So you basically shrink this ball toward this point. That's how you average the contraction with identity operator. So you always have a ball that touching point 1. Therefore, you cannot find a contraction that will entirely contain that ball. Therefore, there's no linear convergence. Now, however, imagine that you have, instead of this inverse lipids, you have strong monotone, then you basically cut the line here. You just basically cut the line here, consider the right side of the line. You no longer have the points that's very near the imaginary axis. That will exclude these points. The points in this set, these points would become away from the boundary. When you have one of the graph that's away from the boundary, composed with a unit circle will give you a contraction. Contraction average with identity will still give you a contraction, except that contraction, the parameter gets worse, but it's still contraction. Therefore, it proves the linear convergence. So basically using simple diagrams, you can show that for ADMM, strong monotonicity is needed. You cannot relax it, but also very easily use those diagrams. You can show for forward backward splitting, you can relax it to inverse Lipschitz operators. Okay, I think I'm running over time. I'm sorry for that, and let me wrap it up. So I basically showed you that this tool is a signature of operators classes. We have defined it. And using just a few diagrams, you can basically get the main ideas very quickly. And on the SRG4 membership, you can you get a rigorous proof. So our paper is here. Welcome to look at it. There are many more examples, including the addition of operators which I have omitted in this talk, as well as other type bounds in this paper. So thank you very much. I will stop here and welcome for questions.
Thank you, Wotao. Thank you very much for your talk. So, time for questions. Yeah, So let me ask a second question related to the age operator. Is there any analytical formulation? Since you mentioned some ways to construct age by using neural networks, is there also a formula, or is just yeah, something which is more implicit?
Oops, I click some button. Let me go to the age. Okay. This H operator. When you, for example, this called DNCNN or denoising CNN.
Yeah.
Is a 17-layer neural network.
Okay.
Where the first 16 layers are convolution layers. The first layer also has batch normalization. Last layer is, I think, it's fully connected.
Okay.
So you basically have 3 parameters doing training. The training gonna choose that parameters. At the same time, you also apply spectral normalization. So the entire DNCN will have that epsilon property.
Oh, good. Yeah. Okay.
So it has an analytic formula. So, which means when you apply this formulation, the speed is really fast.
Yeah. So Team Hoheiser is asking. So team.
Oh yeah, very.
Okay.
That's
Team.
okay.
But yeah. Can you hear us, Team?
Yeah, I can hear
you. Okay, we can hear you. Okay.
Yeah, I think the speaker already read the question.
Okay. Yeah, but.
Right. I have another window, so I keep the.
Yeah, but it's still good to have an interaction, between participants and the speaker. I mean, yeah.
Sure. So yeah, I just wanted to know if you from this very beautiful new tool, do you see any way of looking at acceleration or stochastic variance or second order methods?
Okay, so stochastic method. Suppose you have a finding not just the zero of an operator, but zero of a sum of operators. Actually, just 4 days ago, I was asked this question, and I thought about it. I think it's possible, and I have not write down everything. I have not talked to Ernest yet, but I think it's a deal breaker to do acceleration and the second order method, because acceleration in general involves the function value. The function value cannot be presented as a 2D example. Maybe we go to 3D, we can do it, but it's not clear so far. So negative to most of the question.
So, Zhu Chenlin.
Yeah, I have one more question about H. Can using a neural network-based H speed up the convergence?
We actually did not. I did not run the iteration, so I do not recall how many iterations we need to do in order to get these nice results. I do not know, but in general, because these things have linear convergence, the convergence, it may not be too slow. Usually, it's faster than say then you put proximal total variation here. So probably, I think the answer is the answer.
The iteration converges in 50 to 100 iterations. So with these image processing examples, the rate of convergence of the algorithm is not really an issue. That's not where the competition is. The competition is getting clean images.
Right.
So, Luis Rafael Santos.
By the way, that's Ernest speaking.
Oh, yeah.
Yeah.
Hi, Wotao. Thank you for your talk. Can you use this machinery to prove more than linear convergence, say superlinear or something like that?
Not so far. We haven't tried. No, we haven't tried.
Okay, thank you.
Yeah.
So, then I have another question. So for structure problems, one can write these problems as fixed point iterations in some renormed space. Can you use these techniques in this context?
In which space?
In some renormed spaces. So you do renorming. If you have like composition with operators, let's say. And not just sums, but also compositions. And usually write everything as a fixed point iteration in the do a particular renorming. And the operator you use to renorm, it depends on the linear operator in the problem. And the question is if you can mix these techniques with this approach.
Our paper did for Hilbert space, but Hilbert space isn't. Hilbert space is more restricted than normed space with inner products. We certainly need an inner product because the SRG is defined with that. Right? So I think if the inclusion results can be transferred into a norm space with an inner product structure, I think the results is positive. Yeah.
Okay, good. Yeah, since in that context there is a Hilbert space with the inner product, but this is defined by a matrix. But still, you have everything what you need.
Yeah.
Yeah. Okay.
So in our analysis, what we needed is that the inner product and the space in which the operator properties are defined. So if the operator properties, if an operator is monotone in the usual inner product, then we also need all the other properties to be defined with the same inner product. So we're not allowed to consider a norm with a different norm, whereas monotonicity is defined with the usual norm. We didn't consider that generalization. Maybe it's possible, but that was the inner products have to be all be the same.
Yeah, but this would be important since then you could handle with your method as a primary dual methods and extend the approach.
Certainly. Yeah. It's an interesting future direction.
Yeah. So. More questions? So then, Wotao, thank you very much for the nice talk.
So thank you, Radu.
Very interesting topic. Yeah, very nice talk, and very, very nice new fresh ideas.
Thank we hope that it will generalize to more operators and more spaces. Okay. All right. Thank you, Radu, and thank you everybody for attending my talk.
Just want to announce that we will post video and the slides. And so next week we will have a joint seminar with machine learning online seminar series. And the speaker will be Francis Bach. So same time, Monday next week. So beautiful talk, Wotao. Thank you very much. And,
thank you.
All the best.
All the best.
Okay.
Yeah.
Okay.
Stay safe.
Stay safe. Bye-bye.